Over the break, one of your fellow classmates asked a very good question, and I realized this is something I have to mention to you. Using Faraday's law, we know that once we have time-varying magnetic field, we can create non-conserved electric field, which creates an EMF, right? And we analyze two cases. The first case, where your rotating frequency is omega, and then your induced motional EMF is also having the same frequency. So basically, this is a linear device, a linear system, right? Linear system means you inject certain frequency, and your output is also having the same frequency. But this system, when you have a time-varying rotation of the circuit plus a time variation in magnetic field, and that opens up the potential so you can have new frequencies coming out. So this is definitely a non-linear system. You're in the second year of your program, so probably this is the first example that you encounter a non-linear system, right? You input certain frequency, omega, and your field is omega, but your voltage coming out is 2 omega, right? That is a new frequency. So if you have a system with the capability of giving you new frequency component, that is a nonlinear system, right? Okay, we're moving on to Maxwell's equations. James Maxwell looks like this. He died very young. Okay? If you don't know Maxwell, you probably know this Maxwell. If you like to drink coffee. Okay? Maxwell's equations, there are a total of 4 equations. Don't worry, the 4 equations are very familiar. Equation number 1 and equation number 2 are these two. Nothing new, right? Exactly the same as we learned in the past. Divergence D is equal to the free charge density, and divergence B is always equal to 0. So these two are actually called Gauss's law. And one of the Maxwell's equations is this one, the one we just learned, Faraday's law. Curl of E is equal to the negative time change in B. So what is Maxwell's contribution so that people are willing to give all these equations under his name? Well, basically, in statics, this is called the Amperes Circuit Law, right? Curl of H is equal to J3. Without Maxwell, that equation stays that way. But that is only valid when we talk about static fields. Okay? So basically, Maxwell's contribution to this field is to modify this single equation. But the importance is so evident. People are willing to embrace his contribution and give all the 4 equations under his name. Okay? So this tells me, well, you don't have to be the first person to discover something, but if you can integrate, right, and make the connections so that each and every discoveries are making sense, that's more important. All right? The first contribution, I'm going to explain Maxwell's contribution in 2 aspects. The first one is pure mathematical, which you hate, and I hate as well. Okay? So I'm going to explain his contribution first from the mathematical perspectives, right? Well, curl of H is equal to J. That is coined by Ampere, right? Nothing Maxwell. The second equation is the equation of continuity. This is what we covered for static electric current, right? If you still remember, if you take the divergence of J, the current density, then you actually sense the free charges change as a function of time, right? And Kirchhoff's current law, KCL, is based on this one, but in statics, the time rate of change to the free charge density is 0, right? So divergence of J equals to 0. That is what we learned for static electric current. And that equation reduces to KCL. But now that we're dealing with a time-varying field potentially gives rise to a time-varying charge density. So this rho can be a function of time. And therefore, the partial derivative to time for rho of t is no longer 0. This is what Maxwell realized. Well, if we're no longer in statics, then this derivative does not necessarily need to be 0. So do we have a problem for that? Well, if you still remember, I covered vector analysis in the very beginning. Why? Because they are very useful. So divergence of J, if we also relate the equation of continuity to Amperes law, then divergence of J is equal to taking divergence of this quantity, right? So divergence of J is equal to divergence of curl of H. This is from Amperes Circuit Law. But if you remember, which I bet you don't, anyone still remember what this is equal to? You have a vector field, you take its curl, you're trying to evaluate its circulation, and then you take its divergence. What does that equal to? I'm hoping someone can respond. For the 6th time, I'm still hoping. I'm very patient. Before I retire, there will be one student responding to this question. Please? 0. Oh, finally. I don't have to anticipate anymore. Thank you. Why? Because this is one of the 2 null identities that occur. Right? When you take the curl, you're trying to find the component that circulates closest upon itself. Therefore, when you take the divergence, there's no field coming out, right? That is how I touch. So this is the vector identity for any given vector. You don't expect this term to be non-zero. But now that Maxwell found there is an apparent contradiction between these 2 equations. So basically, Amperes Circuit Law was valid for statics. Equation of continuity in statics was fine, right? Because this term is 0. So under the statics consideration, this is not violated. But now that we're saying, well, rho of t is permitted, then this vector identity is violated. 违背, okay? So how can the null identity be violated? So that's a major question Maxwell asked more than 100 years ago. Well, apparently he's very good at math, right? I don't care. Violates, well, fine, it just violates. Okay. So this is the decisive point. Let's imagine we were in 18-something, right? and we see this potential violation, then you need to think which equation needs to be modified. Do you want to modify this one? Or do you want to modify this one? Or you want to modify this one? So the new identity is, what's wrong? Do you dare to say that? Okay, so apparently Maxwell was very fond of math. He knew that math is the higher governing law, right? So he's not challenging this one. Okay. It's like professor says, your senior student says, you usually obey your senior students, 学长学姐, right? You don't obey the professors. Professors are like this. Right? Senior students are like this. So basically, he is saying that this is the highest governing rule. I'm not going to challenge this one. So something wrong with maybe either this one or this one. Okay. So let me write down this contradiction. Divergence of J is equal to divergence of curl of H, and is equal to the negative time variation of rho of T. Okay? Now, this is a decisive point. Maxwell was very determined this cannot be changed. So, the divergence of a curl of a vector field has to be 0. So now you are at a turning point of your career. You can become famous. Okay? What do you do? Look at the equation. What do you do? What do you only have to do? So that divergence of curl of H is again 0. Well, you erase this one, right? When you move this guy to the left-hand side, this becomes 0, right? Genius are usually based on very simple modifications. Oh, you have, I suppose, I'm very sure everybody here in the room can do this, right? Moving one term from the right-hand side to the left-hand side, so this is again 0. Well, that's exactly what he did. Really? Really? So you're not scratching your head. Well, what's so profound of that? Okay. But at this moment, purely mathematically, he resolved that contradiction, right? So mathematically, divergence of curl of a vector field is again 0. Fine. But his real contribution is the following physical explanation. Okay? This is just his starting point. He realized mathematically you had to move one guy from here to here, but then he also found out the physical meaning and the importance of this term. Okay? Up to now, it's still very not obvious, but if you still remember, he borrows another result from another guy. And finally, he realized the physical meaning. What is rho? Rho is divergence of D, right? So he again borrowed from Gauss. Divergence of D is equal to rho. So now we look at this new equation. What have we learned? is J? What is J? J is the free current density, right? So if you were Maxwell and you derive to this point, how would you call this term? This is a current, right? Amperes law is saying that, well, if you have the magnetic field, then you have current. Why not call this also a current? That's a physical meaning, right? You look puzzled, but let me try to explain the situation in a different way. In physics, the same problem is converted to be able to explain how a capacitor works. Well, we all know that if a capacitor is connected to a time-varying voltage source or a current source, it works, right? It works. But how does it work? For this simple circuitry to work, if you have I of t, you have I of t, a closed loop driven by the source has to have the same current everywhere, right? But what's current? Well, current is basically number of charge over the measurement time, okay? So the real contribution by Maxwell is more than just mathematical derivation. He was actually able to use this multiplication to explain one unsolvable truth. If you have a capacitor here, if you draw the cross section, you can count how many charges are flowing across it, right, over 1 second. And that's called the current. But if you have some measurement device here, what is the number of charge flowing across your device per second? How many charges do you anticipate? None, right? But this device works. So in the center between these two metallic structures, you don't have charged particles flowing across it, but only on the two wires. But it is working to conduct current. So that's really puzzling. That's an unsolved puzzle. So what is happening is, where's my yellow chalk, right? Suppose you have a positive charge flowing in. When the positive charge meets this side, the left-hand side of the capacitor, it cannot swing across, right? It cannot. So how to explain this entire device or entire system works so that everywhere the current values are the same? Well, it's not so difficult. If you really understand it, if you have a positive charge coming out to this left plate at the same time, you have a negative charge flowing in a reverse direction, moving towards the right-hand side, right? Well, both charges cannot swing across, but what do? They set up field lines. Okay? Basically, Maxwell is trying to revisit how a capacitor works, but in a time-varying sense. So what does that mean? It means if I have a time varying of charges on the wires that's giving rise to I of t on the wire, let's call it W. But when the charges reaches to the capacitor, they can no longer move. So spatially they can no longer move. But if you add one more charge, you add correspondingly one more field line. So this field line variation can actually be viewed as current source. Okay, that's the physical meaning of this term. Divergence of J is telling you how many real charged particles are swimming across your detection surface per time. So these are really due to the charges moving. But this is saying that the field lines, the variation in the number of field lines in certain time is equivalently called a current. Okay. And that is called the displacement current. Particles are not moving. It's only the field line that is increasing or decreasing, and that effectively is equivalent to a current term. Therefore, this term is called the displacement current, JD. Right? Since we have divergence, we can combine together. So this D as a function of time, and you evaluate its time variation, that is JD. So Maxwell's contribution is finally people are able to explain how this simple device or system works. Even though you cannot have charged particle moving across these two parallel plates, but they only need to rely or connect by the field lines, right? So equivalently, you have I wire of T, but here you have IC capacitor of T equal to I wire of T. So the current remains continuous on each position within your loop. And that really requires adding this additional displacement current term. Otherwise, you're not able to resolve the operational principle of a simple capacitor. Okay? So, the way I introduced Maxwell's equation started with some kind of naughty joke, but eventually, after all this explanation, I believe I have somehow conveyed Maxwell is really worthy to be remembered, right? So although he only modified one single equation, but he integrated everything and provided you a full knowledge, a full picture, right? So people were willing to donate all 4 equations under his name. Right? So basically, this is the only modified equation. So it's called the modified Amperes Circuit Law. Whenever you have time varying fields, remember, curl of H is now equal to the free current density, the movable charges, plus the time varying electric field lines. Okay. So that red is called the displacement current. Okay. It does not rely on moving charges, but only the time variation of the field line, electric field lines. All right. So this is really, the problem he resolved. Charge cannot just swim across vacuum. Okay. But still, we have to know that on an operational circuitry, location by location, you have to have the same current. So that is only possible by denoting this term, as the displacement current. This is called the displacement current density. Okay? You have to perform a surface integration to become current. Okay? So del D del T is only the displacement current density, right? This is current density. This is also current density. But once you perform this closed loop integration, here you have the surface integration. So now you have the free current and you have the displacement current. Okay? All right. So the same question, so assume we know the driving voltage across this capacitor. Let us prove point by point on all locations on the circuitry we have the same current. Well, parallel plate inside, once you know the applied voltage, you know the E field, right? V equals ED. So the E field as a function of time is your applied voltage divided by the distance. Well, once you know E, you know D, right? All you have to know is what material is used to separate the 2 parallel plates. Basically, you want to have a nice dielectric material with epsilon permittivity. So that is your D. Then your displacement current is the surface integration of the time variation of your D field over the entire surface. Okay? So that is C1. Basically, this is your capacitance, right? Capacitance and cosine of T. But we also know that from electric circuits, well, if you have an operational capacitor, you know it's I once you know how your voltage changes. So basically, that is the direct proof. You have an operational circuitry based on one single capacitor, and point by point on the wire or inside the capacitor, you have the same current value. Okay. You cannot have this result without the added term of the displacement current density. And that term was realized by Maxwell because he found out the vector operation, the null identity, was violated. Okay? So, yeah, you have to give credits to math. Okay? And once you know the E field, or you know the current, you can find the H field. Right? Amperes Circuit Law. So if you go into details, location by location on the circuitry, you would have continuous voltage, you would have continuous current, you would have the same E field, you would have the same H field. Okay? H field, you have H field outside of the capacitor and also inside. Okay? All right. Finally, the entire semester in front of you. For the entire semester, pretty much we only learned 4 equations. First one, Faraday's law, right? When you have time varying fields, curl of E is no longer 0. In differential form, this is Faraday's law. In integral form, okay. Well, luckily, Gauss's law remains unchanged. Okay. What Maxwell did was to add the displacement current density. So he modified Amperes Circuit Law. So that is called the modified Amperes law. Right? Last equation, divergence of B equals to 0 remains unchanged. So these 4 equations are together called Maxwell's equations. Right? Okay, boundary conditions. Let me ask you one question. In static fields, we investigated the boundary conditions, right? For all 4 fields. Whenever you have divergence, if your field quantity is related to divergence, then you know boundary. When you have material 1, material 2, you have 2 materials, you form 1 interface, right? Whenever you have a divergence law, divergence tells you how the normal components are related. Okay? So if you have a divergence, this gives you the normal component. AN1 versus AN2. Okay? And whenever you have curvature relation, then you know how the tangential fields. AT1 versus AT2. Okay. So let me ask you directly. Even though in the presence of time-varying fields, for the 2 divergence laws, nothing is changed. Do we really need to investigate how the boundary conditions are changed? Meaning, in the past, divergence of D equals to rho, and D and rho are both not functions of time. But now, D is a function of time, rho is a function of time. So divergence of D of t equals rho of t. Do we need to reinvestigate how the boundary conditions are changing? Really, no, because the entire equation is the same. Okay? So for these 2 equations, nothing is changed. But this equation and this equation are heavily modified, right? Initially, curl of E is equal to 0 in statics, but now you have time-varying fields. This is non-zero. You added this temporal derivation term. So you need to reinvestigate how the boundary conditions have to be modified accordingly. And also this term, you added a new current source, right? So you think, oh, in time-varying fields, I need to remember another set of boundary conditions. But luckily, these 2 are both curl relationships. So that tells me I only have to remember two new tangential field relationships, right? The normal components are due to divergence laws. The two divergence laws are not modified. So luckily, we know this already. Okay? Is that true? Is the professor so cruel? You have to remember new boundary conditions for static fields and time-varying fields? Let's let mathematics talk. Okay? Let's look at the equation we modified. Well, Faraday tells you if you have time-varying magnetic field, you create EMF. But think about it. Curl of E, you're integrating that over a loop, right, with surface. So over to the left, you have a closed loop integration because you have invoked Stokes' theorem. But actually over to the right, you're evaluating the surface integration. Surface integration. So you have to think, whenever we form this interface and we form a closed loop, over to the left, we're trying to evaluate the tangential component of E over this entire closed loop. Over to the right, now that is non-zero, so we do have to evaluate the total magnetic flux and its time variation over this area, right? But do we really have to evaluate that? If you still remember, in the past, we always made this height of the rectangle approaching to zero. So if this delta H is zero, what is my area? Zero. Okay? Which means, luckily, boundary condition is not changed. For Faraday's law, even though under the presence of time-varying field, your boundary condition remains unchanged. It's still E1t equals to E2t. Okay. What about the modified Amperes law? Now that you might have displacement current density, but again, over to the right, you're integrating over the entire surface, this surface. You can make your surface to zero, right? Simply by making delta H to zero. So in the end, nothing is changed. Okay? So the happy message is, even though now we're moving into time-varying fields, all four boundary conditions remains valid. You don't need to analyze or you don't have to memorize anything new. Due to the fact we can arbitrarily select the loop to be just the line on the interface. Okay, so nothing's changed. Nothing's changed for these two modified Clerk equations, and regardless to say, the divergence equations are not changed. So of course, they remain to be the same. Okay.